All right. Welcome to this Apache Hudi meetup, folks. My name is Nishith, and I manage the data lake storage team at Uber. We have three very interesting talks lined up for you guys from Uber, AWS, and City Storage Systems. Each session will be followed with a Q&A session. So please add your questions to the Q&A box at the bottom of the Zoom, and we'll answer them. So let us get started with the first session of the day. Over to you, Prashant and Satish.
Okay. Hello, everyone. I'm Prashant, and I also have my, just a second, okay. I also have my colleague Satish with me. Both of us are developers in the Uber Data Lake Storage team, and we both are also Hudi committers. In this presentation, I'll be taking you, both of us will be taking you through some of the notable release features of the 07 release, which are particularly important to us at Uber and which we are planning to use. We'll also talk about how we have tested these features at scale and how we are releasing them into production. And finally, we'll take you through the roadmap of Hudi at Uber. So the 07 release brought out several notable features, out of which our engineering team at Uber was a big contributors to the three of them. One was eliminating file listing, also known as RFC 15. We also contributed to the data clustering work and to the insert override support. All of these three features we are currently releasing in production within our data sets. And we are also looking towards the Spark 3 support and the Flink support, which was introduced in 07. We are still studying them and we'll be using them in the future. So the file listing enhancement feature was a particularly important feature for us because of a very large Hudi deployment at Uber, due to which we had very large load on the SDFS infrastructure, especially on the name nodes, due to the large amount of file listing calls and the other API calls which are issued by Hudi. So with this file listing enhancement feature, in a nutshell, the file listings of the partitions as well as file within the partition is saved within an internal table in Hudi, thereby saving on the cost of sending those API calls to the name node. And also it makes several operations faster because you can do this listing faster by listing them, by reading them through this table rather than having to depend on the name node. And we are in the process of deploying this in our production, thereby uh, thereby taking the benefit of this whole infrastructure. We also helped design this and test it at scale, and we are looking into newer uh, features built on top of this. For example, secondary column indexes and record level indexes, which are also in progress in design discussions. So because of such a large scale deployment at Uber, there are some specific challenges we have while testing and releasing new features. So this slide should give you an idea of what the deployment at Uber looks like. And given the very large number of tables and the amount of data we ingest every day here, we have very specific or very specific testing challenges at this scale. Some of them are related to the resource limitations, like we are unable to uh, create multiple copies of these petabyte scale databases just for testing. Other are related to allowing multiple developers to test with these large data sets. And finally, we also have the challenges of testing new features before we release them, and to test whether they will work at scale properly, or to uh, or to recommend the appropriate settings for many of these data sets without having to change the production every time and see the effects of that. So that's the lack of the A/B testing which we were facing an issue with. So in the 07 release, to deal with many of these testing challenges, we created a new testing framework which we call the Hudi replay testing framework. It's an extension of a Hudi test suite, which already exists in Hudi. And this allows taking existing commits on production data sets and replaying it back onto the same production data sets in a non-destructive manner. And in this way, we take realistic data, which is already going in our production. We replay it back, maybe by changing different settings or using a different Hudi version, and we measure it and compare it to what happened in production. So this way we can test various settings and new features on our existing data sets, and multiple engineers can do this testing together without having to create copies of those data sets or without having all of those challenges which I mentioned earlier. So the main idea behind this testing framework is the use of an overlay file system. And this is an idea inspired by overlay file systems in the Docker world or in the Linux VFS world, where you take a file system and you use it in a read-only manner, and all the changes on that file systems are saved in a temporary location, and you use both of these file systems together and union them together to give a view to the outside world. So in this case, we have an overlay file system which we have created, and this file system uses the actual production data sets in a read-only fashion and snapshotted at a particular time. And it also has access to a temporary location where it performs all the writes and the modifications as required. And to the rest of the Hudi code base, this looks like a normal Hudi wrapper file system kind of implementation. And the Hudi code base is unaware of that underneath we are using this overlay file system. So the benefit of that is very realistic testing, because we are actually performing all our testings on the production data. The testing is very fast because we do not have to bootstrap data sets. We don't have to use resources uh, to create new data sets, and multiple people can test at the same time because everyone has a different read write or the temporary read write location, and they all use the same production data set for testing. And the framework works in 3 steps. So in step 1, we decide which commit from the actual production data set we want to replay and test. So in step 1, we'll read the original commit metadata, and the original file system is smart enough, the overlay file system is smart enough to know where a particular read is existing, whether it exists in the production data set or whether it exists on the temporary data set. So temporary data location. So in step 1, we'll read the original commit metadata from the production data set, which is working through an ingestion pipeline in production. Then we will process that commit metadata to figure out all the records which were inserted, upserted, deleted as part of that data set. And this will be the large number of records which went in the production pipeline. And then we will process that to actually read the same records from the various Parquet files sitting in our production directories. So that is the step 2. And we create an in-memory, not an in-memory, we create a RDD out of all that data. And in step 3, we just use the Hudi write client APIs to insert that data or replay. This is the replay part back onto the same data set. But in this case, all the new Parquet files, all the new instant files, everything is created only on the temporary location and using the overlay file system. So we never change anything on the production data set, and all the changes are written to the temporary location. And we are trying to enable all the Hudi test suite functionality into this framework. Currently, even the clean works, so we can perform clean on the production data set and no file is deleted, but markers are saved in the temporary location to signify that a particular file was deleted. And with this model, multiple developers can test at the same time, and we can do A/B testing. We can change a feature or a setting in Hudi. We can enable a feature. We can disable a feature. We can see and measure stats while replaying the commit and compare it to the production commit and figure out that whether this was beneficial to us or to a particular data set, or whether this led to some issues. And we have solved a lot of our testing challenges in using this model. And for the 07 release, we have used this framework extensively to test the new features which we are releasing, as well as to figure out certain bugs or regressions which were caused uh, which led to some performance issues for us. and we have been able to fix them even before releasing into production. So this has been very useful to us for the 07 production release. Now I'll hand it over to my colleague Satish for the rest of the presentation.
Hello, everyone. Let me share. You guys can see my slides?
Yeah.
Hello, everyone. I'm Satish. I'm going to present another new feature we added in the latest Hudi release. This feature is called clustering. So at a high level, clustering is a general framework we developed to rewrite data for efficiency and compliance reasons. Let's look at some use cases. One of the primary goals of Hudi is to bring stream processing to big data. But for copy and write tables, this requires writing small files to improve parallelism in the write path. But typically query engines and some distributed file systems like HDFS perform poorly with a lot of small files. So we added a strategy in clustering to stitch these small files into large files, and the data is available to the queries sooner because even the small files are like that. There is a limit to the number of small files, and so the freshness is improved. But at the same time, in the background, we can stitch these small files together and improve the query performance for older data. The other use case is to improve data locality. So typically data is stored based on arrival time in data lake, but queries perform better when the frequently queried data is co-located together, because typically this enables like efficient pruning. So we added another strategy in clustering to sort data based on the specified columns and improve query efficiency. Similarly, for storage efficiency, we want to rewrite data using different compression algorithm or remove certain columns. So all this improves the storage efficiency, and especially with a large scale deployment at Uber, this has proven to be like very useful, very efficient. Lastly, for compliance reasons, we also had to have use cases to encrypt data after certain days or delete certain data after some time to restrict access or to comply with the local regulations. So overall, at a high level, clustering is basically a general framework where users can specify the transformation logic, and clustering does rewrite the data in a Hudi way, providing like snapshot isolation, time travel, atomic commits, and also improving operations. In the open source, we provided the first two strategies to improve freshness and data locality. And the remaining ones are work in progress for Uber internal use. And let's take a closer look at one of the use cases of clustering to improve the data locality. So the first row here is basically showing the ingestion path typically, right? So when we have data coming in, based on the arrival time, we create multiple files on the distributed file system. So in this case, one of the most frequent queries is based on the session ID. But this information for the session ID is spread over all these files. So what happens is when users query for this specific session ID, the query has to essentially process, in the worst case, process all these 10,000 files. Now let's look at the next row. This example shows how clustering works. So we have the same initial data set with 10,000 files, and this data is based on arrival time. But when users can request to cluster data by session ID, so what happens is that the entire data in this partition is sorted by session ID, and so the number of files having this session ID will be 1 or 2 in the worst case. So this improves query performance significantly because now the query engines only need to process and read one file. So the remaining files are efficiently pruned from the query plan. This is an example from a small production data set with 200 gigabytes of data. So we ran the same query basically for querying for a given session ID. And without clustering, the query took 130 seconds. and processed all the 20 million records. Whereas after clustering, it only took 55 seconds, and it only needed to process like 110K records. So this achieves like up to 50% performance improvements for this use case. And setting up clustering is also very straightforward. So this example shows for inline clustering how to set it up. Basically, we need to add three important configurations, whether we want to do inline clustering, and how often do you want to run the clustering, and the target file size if target file size after clustering, so to eliminate small files. If you also want to sort the data, you can also specify optional list of columns, and the data will be sorted globally within the partition based on these columns. We also have async clustering. So for more advanced use cases, you can refer to the wiki page here. I think the slides will be shared later on. Looking forward, there are actually a lot of improvements we can do on clustering. So one of the use cases is to improve efficiency. So like I mentioned, there is a strategy to stitch files together in the clustering framework. And that approach today reads and writes the entire data, so incurring a large amount of cost for serialization and deserialization. But there's an efficient way to stitch these files together without incurring that additional cost. So that is work in progress. The other one is rewriting as a service. This is a very interesting use case to basically schedule this rewrite during non-peak hours to make use of unused hardware, essentially. Also, the service can look at the past historical queries, look at the data patterns, and suggest new patterns for improving the efficiency, because a lot of times users are not aware of the optimal layout. So this is something the service can suggest. Also, there are some use cases where rewriting data is not possible. So we also want to support use cases to improve data locality during ingestion. And this can be done by providing a pluggable partitioner strategy in Hudi. So that's with respect to clustering. But we also have a very interesting roadmap. So some of the important work is highlighted here, supporting concurrent writers at the same time, taking advantage of Hudi's multi-version concurrency control, improving the observability and auto-tuning these jobs because the configuration can sometimes get complex. So we also want to add auto-tuning support. We also want to support other file formats like ORC. And Hudi already provides an indexing mechanism, a pluggable indexing mechanism today, but we want to add more optimal indexing techniques for both primary key and secondary key. And this is being designed right now. So yeah, we have a lot of interesting work, and we are looking to expand our data lake team at Uber. This is also one of the fast growing fields. So if you're interested in contributing, please send your resumes to data-lake-jobs@uber.com. And a big thank you for the open source community for helping us release this big feature set in 0.7 release. If you are interested in collaborating, contributing to open source, please reach out. The website is hudi.apache.org. And there is also a community link there. You can engage us through Slack. Yeah, that's all. If you have any questions, please add it to the Q&A box at the bottom of the Zoom.
All right. So I think those were great slides, Prashant and Satish. Thank you. There are a few questions. I think one question which is already answered is you have more than 8,000 tables in your data lake. How do you process all these tables? Do all these tables have their own Spark jobs? Do you use threads to process multiple tables in the same Spark context? So I'll just read out the answer from Prashant. We have both these models. Tables which have very large number of records ingested have their own independent pipelines. And some pipelines process a group of tables using multiple Spark jobs created and monitored. So the next question is, can we presume clustering is similar to bucketing? Save files with same file ID on the same file, or how does it compare?
So clustering, I would say, is a general framework to rewrite data after ingestion has happened. Bucketing, as far as I know, is basically improving the data locality during ingestion itself. And bucketing also typically has like a static partitioning mechanism that doesn't really work well for large scale deployments in terms of operations. So there are some differences. Also, I'd like to highlight that clustering is a general framework. It's one of the strategies is to improve the data locality, but there are other strategies like I mentioned for stitching files and for basically compliance reasons, rewriting data for compliance reasons.
All right. Next question from Jim. With secondary indexes and multiple concurrent writers, Hudi is becoming a full-blown database. Do you agree with this?
I feel it's becoming similar to a full-blown database, but there will always be some differences, and it depends on which database you are referring to in the comparison. For example, even with the secondary indexes, the indexes will not be that granular like in a full-blown database like say MySQL or MongoDB or anything, because of the limitations of the amount of data and where you are saving the data. The data is available on file systems which are not directly connected. So you always have to optimize for reading less and you cannot save everything in memory. So it is becoming similar to that, but not completely. Anybody else has a different view on that?
I think that's a fair answer. So the next question, for the replay test framework, does it have more enhanced functionality, like give a recipe to replay n number of commits? That's the first part. The second part, is it possible to replay with some lag? I assume we don't want to do writes to prod datasets, but can we use replay test framework to say replay everything for the next few hours with some delay for commits from a prod dataset?
Right. So we are developing all the functionality as required. So we currently have a way to replay one commit, do a clean, do a rollback, but we do not have the functionality of replaying multiple commits and then doing something else. So currently it supports one commit with other operations in after that, but not multiple commits. But these are all different features which are very easy to implement on top of it. So we are developing it as we go based on what features we are testing or what specific our testing requirement is. And as for your second part, that is it possible to replay with some lag? Yes, sure. You can. All you need to, I mean, it's very easy to do because you are running this in a Spark. It's technically a Spark job, and it can I mean, you can introduce a Hudi test suite DAG node, which could be for a delay, and then continue doing other things. So anything which you can do in Hudi test suite or you can invent in that can be ported over to this framework.
Sounds great. I think those are all the questions we have. So thank you, Satish and Prashant. All right. So so the second talk is from AWS, which will cover the Hudi EMR offering, the contributions they've made to help productionize workloads for customers. So over to you, Udit and Venning.
Let me share my screen. Hi, everyone. I'm Wenning. Udit and I are both software engineers at Amazon EMR, and we are Apache Hudi committer as well. Here we are going to talk about Apache Hudi and EMR. In this session, first we are going to talk about how Apache Hudi is integrated with EMR, why we support Hudi, and how some of our customers use Hudi to change data capture. Then we go on to talk about how Hudi integrates with other AWS services besides EMR, and the contributions EMR team made over the past year and our roadmap ahead. Let's see how Hudi is integrated with EMR. As most of you might know, Amazon EMR is a cloud-based big data platform offering most popular open source software such as Spark, Hive, HBase, Flink, and Presto. We added official support for Hudi since November 2019 with EMR release 5.28. Now, with our latest release, you have Hudi 06 available. Hudi in EMR integrates with Spark, Hive, Presto, and Trino. To manage metadata for Hudi Hive tables, customer can use Glue Catalog or other external databases like Amazon Aurora. To give more details, EMR releases are snapshots, which means each application version is fixed in each release. We try our best to deliver the latest and greatest version of each big data application. Supporting Hudi requires us to configure Hudi binaries present at the relevant class paths of the applications supporting Hudi. In addition, we configure other Hudi utilities like CLI, Hive sync tools, etc. At EMR, we usually build our own Hudi based off the latest open source release version. We usually have some additional backports for critical fix, and we have some EMR specific fixes as well. EMR also make lots of changes in other applications like Spark, Hive, Presto, and HBase. So it's important for us to make sure that Hudi could work with our internal versions of these applications. To achieve this goal, we have nightly builds and integration tests run to get notified if changes to other applications break our Hudi. As much as possible, we try to contribute all our changes back to open source Hudi. Here are some key reasons why we add Hudi in EMR. Customers can do change data capture and be able to apply change logs to their S3 data lakes, which supports upserts and delete in a transactional way. They can also comply with privacy regulations like GDPR that enforce people's right to remove their user data. Also, Hudi can help you do near real-time ingestion with right-optimized data format and automatically manage file sizes. And besides, it has query support with Hive and Presto, which is an added benefit that can help. Let's see how some of our customers do change data capture with EMR and Hudi. This is an example of how to capture changes to data from an upstream Amazon RDS for MySQL using AWS Database Migration Service, and then apply those changes to a dataset in Amazon S3 using Apache Hud on EMR. AWS Database Migration Service is a web service that you can use to migrate data from your database to AWS databases, or even to S3. So in the first stage, DMS service will capture all the changed data from RDS and then export them to S3 in Parquet format. And then the Hudi Delta streamer running on EMR will apply the change logs to your Hudi dataset on S3 and perform insert, upsert, or delete depending on the changes. The previous example ingests file-based changes, and this is a streaming-based example for doing change data capture. As you may know, Debizoom is an open source framework. It's a distributed platform for change data capture and has connectors to feed database messages into Kafka. In this example, Debizoom running on EC2 instance is able to capture change logs from Amazon Aurora database and then sync them to a Kafka topic in Amazon Managed Streaming for Kafka. And then Hudi Delta streamer running on EMR could continuously consume the streaming from the Kafka topic and finally write them into S3. Now let's see how Hudi is integrated with other services in Amazon besides EMR. Once you have a Hudi dataset on S3 and register it as a table with AWS Glue Data Catalog, you have multiple choices to query Hudi table. Amazon Athena is a serverless interactive query service, which allows you to query the rate-optimized view of your S3 Hudi dataset with a user-friendly interface. Also, Amazon Redshift Spectrum, a feature of Amazon Redshift, enables you to query Hudi dataset directly from your Redshift cluster without first loading the whole data into it, minimizing time to insight. Note that currently both Athena and Redshift does not support snapshot queries for merge on read table. And of course, you can always use other big data applications like Hive or Presto in EMR to query Hudi. Here is an example of a completely serverless pipeline that lets you to do CDC using AWS DMS and Glue. Amazon Glue is a serverless, fully managed, and cloud-optimized ETL service. Since January this year, AWS Glue has added official support for Hudi by introducing a custom connector. This custom connector makes it easier to create and ingest dataset in Hudi format to S3 via AWS Glue. And customers can easily configure their personalized workflow via Hudi data source API in Python or Scala script. In this example, DMS publishes the change logs in Parquet format to S3, which is consumed by the Hudi jobs running in Glue, and then ingest the data in Hudi format on S3. The Hudi dataset can then be queried via Athena or Redshift Spectrum. Here is a Python code example that is able to load data into S3 dataset using Hudi Bark insert via Glue. First, it loads the data into a Spark data frame, then defines the Hudi configurations for the job, where we define the Bark insert operation. Then we pass the date frame to Glue context to perform the Bark insert, and the customer connector would help to create Hudi tables in AWS Glue data catalog and automatically add partitions when new data is added to the partition table. Next, I'll let Udi to continue the presentation.
Okay, thanks, Wenning, for that presentation. Let me try to share my screen. Okay, so now let's see the what Hudi feature work and the contributions we have made from EMR side over the past year. So one of the things that we really care about at EMR is to make sure that we provide the latest versions of all the open source applications. So Hudi in this sense is particularly challenging to support because it has dependencies on several other open source applications like Spark, Hadoop, Hive, and all of these applications are evolving fast, and we ourselves are making plenty of changes in these applications. So we need to constantly make sure that Hudi is working with the latest versions of these applications. And in this process, we have been able to contribute several important upgrades to open source Hudi as well. In the picture here, you can see how Hudi and its other dependencies have evolved at EMR over the last few releases. With our latest 6.02 release, we support Hudi 060 with the latest Spark 3 and Hadoop 3 and Hive 3. Those were the latest which were available at the time of the release. Okay, so some of the upgrades that we did over the past year were we initially upgraded to Spark 2.4.4 from Spark 2.1, I believe, for Hudi. In that process, we did a bunch of other cleanup. We upgraded to the native Spark Avro module with Spark for its Spark to Avro conversions. The deprecated Databricks Avro had a bunch of issues. We upgraded to Avro 1.8, and in all this process, we were able to support decimal and date types natively via Hive. Earlier, they would be synced as strings, but now they could be synced as the native types. We upgraded the Docker test to run with Spark 2.4. More recently, we added support for Scala 2.12, so you can compile with either 11 or 12 now. And our most recent contribution has been around adding support for Spark 3. Again, you can build, by default, it builds with Spark 2. Now you can build with Spark 3 as well, with just a profile change. As part of the Spark 3 upgrade, some of the major work went in around making sure that our bulk insert implementation, which is data source v2 based, it is able to work with Spark 3 because data source v2, as you know, was still experimental and they evolved a lot of their APIs in Spark 3. So some of the upgrades that are not yet in open source are Hadoop 3, Hive 3, and HBase 2. We internally have it in EMR. We have contributed a few things, but the complete upgrades are yet to be done. So one of the main features we worked on last year in collaboration with Uber team was to basically provide an efficient way to migrate large data sets over to Hoodie, especially for customers who have like large data lake installations with terabytes and petabytes of data sitting on S3. Now, using a traditional bulk insert operation is uh, not very efficient in this case. It is very time consuming and involves a lot of compute power and high read and write cost. And the main reason for that is basically Hoodie would rewrite the entire data set as part of that, in addition to generating the metadata and the Bloom indexes which it needs. And in the process, it has to, get the data frame, convert it to an RDD of records, and then repartition, and then finally write all of it, which is very expensive. Uh, so, uh, okay. So basically, we went ahead and introduced a more efficient one-time operation called the bootstrap operation that customers with such legacy data lakes can use. So essentially, the idea behind it was that we decouple the Hoodie metadata from the actual metadata. So as part of this migration operation, Hoodie will just write metadata files, which will contain the per record metadata columns and the Bloom index, whereas the actual data is not copied over and it's still served from the source location. It is eventually and incrementally copied over to the Hoodie table as and when you do an upsort or delete on your data. And there's this one-to-one mapping between your source data files and your metadata files. And this mapping we maintain in an H file index within Hoodie metadata itself. So you can do efficient random lookups based on a partition or a file group level. You can get the mappings easily. And this is basically used on the reader sides when, for example, query engines need to query a table which is in bootstrap mode. Uh, so it will require a merging of the source data and the metadata at runtime to give you the complete view of the data set. So here's a quick snapshot, quick code snippet of how you can do the bootstrap operation using the data source API. Essentially, you just specify bootstrap as the type of the operation. You specify a source path and your Hoodie table path, and you perform it using the data frame. Now this data frame here, you can notice it's an empty data frame, and that's essentially because Hoodie will internally, go over the source data file by file and try to generate the corresponding metadata files for you. So you don't have to load and give the data frame to it. And this feature you can operate in two modes. The default mode is and basically these modes can be configured at a partition level using regexes. So the default mode is the metadata only mode, which we have already discussed, where Hoodie will basically just generate the metadata files. And the other mode is the full record mode, where it will copy the actual data over as well. So the reason for providing two modes was that essentially, like if you have certain hot partitions where your queries will hit more often just after migration, so you can migrate those partitions, with the full record mode, so you can avoid the additional read cost of merging the source data and the metadata at read time. So yeah, we worked on this feature in collaboration with Uber. Our contributions were more on the data source side of things and the query engine side of things to make sure the query engines can query a bootstrap table correctly. Uh, One of the main works we did was around implementing a new Spark relation in Hoodie Spark data source. Now this relation can essentially, it can basically use Spark's native Parquet readers itself to read the source file and the metadata file and give you the results. So we don't have to fall back on like the Hive input format and stuff, which is quite inefficient. We implemented similar stuff in Presto as well, and a bunch of other things. This graph here shows a quick performance test that we ran on a 1 TB data set sitting on Amazon S3. So as you can see, like a bootstrap operation for this particular cluster setup and data set, it performed almost 5 times faster than the traditional bulk insert operation. And it is significantly faster than bulk insert v2, which went in Hoodie 060, which is based off data source v2 as well. Okay, so the another important feature we worked on was support for snapshot queries with PrestoDB. This was a lot of customers had asked for this feature on our side. So this slide here, it shows how the read optimized queries work and what we had to do for snapshot queries. So to quickly go over it, for the read optimized queries, basically it was much easier to support. We could simply rely on Presto's native Parquet readers itself to do the read for us. All we had to do is basically inject this hoodie's path filter in Presto. So when it does the listing, it can use this path filter to filter out the latest commit files. And then we let Presto internally form its file splits and pass it to the workers, which can then read it using native reader itself. Now, the problem with snapshot queries was that you have to merge the base Parquet file with the Delta files, and then you have to provide the results. Now, in addition to that, the Presto's high split concept, it does not understand these splits as well. It's basically like similar to the Hadoop file split where you have just one file with some byte ranges for that split. It doesn't understand the log files. So in order to support this, we decided to reuse the Hive input format implementation that we have for the merge on real-time tables, because it essentially gets those kind of splits for us with the log files, and then it can do the read using its record reader. So basically, to get this done through Presto, we had to basically hook Presto to bypass, in case of merge on read tables, to bypass its own internal split generation and use input formats get splits function to basically get all these hoodie real time file splits, so to say. And then we introduce these converters in Presto, which convert from and to real-time file splits to Presto's Hive split representations. And in that representation, we had to, add some fields, which so that we can add this additional information about the log files, for example, so it can serialize and pass it to the workers. And then on the worker side, once you have the Hive split, you can deserialize it back into the Hoodie real-time file split, and then you can read it using the record reader from the input format itself. So this has been implemented in a fairly generic way. So like any custom split or custom record reader you want to use with Presto, you should be able to use. Essentially, all you'll have to do is like implement these custom converters, which can convert to and fro from Presto's Hive split to your whatever custom split you have. And similar concept we used for even bootstrap tables as well, because there also the splits are slightly different. Each split has a source data file and the metadata file as well, which need to be merged. So we kind of followed similar approach there as well. So another thing that is absolutely crucial for us at EMR is to make sure Hoodie is performant with S3. So one of the things that we hit last year was that a lot of customers' performance was being hurt because of file listings. uh, So listing all the complete data set sitting on S3 is extremely expensive. Essentially, you will have to go over all the partitions of your data and do list calls for basically order of n list calls for each of the partitions, basically. So, and Hoodie actually performs this listing of the whole data set at various code paths. For example, it needs to get like all the partition paths in your data set. And that happens in the compactor cleaner, and if you use a global index or you use HiveSync, all those code paths actually need to get all the partition paths. And how it identifies partition path is by literally checking like the presence of Hoodie partition metadata file in all those partitions. Uh, Similarly, like on the query engine side, if you do like a partition agnostic query, it's gonna hit most of all the partitions, and it's gonna fetch all the files. So this was becoming really a bottleneck with S3 performance, and it would even hurt HDFS performance, as Uber team mentioned. It would affect the stability of the name node because of a bunch of list calls. So our initial mitigation, at least for S3 thing, was that we try to parallelize this as much as possible. On the writer side, we try to use like Spark context to distribute the listing across the cluster as much as possible. uh, on the Spark data source relations that we implemented, we tried to relay all this to Spark's in-memory file index implementation, which again does it in a distributed way and has some other nuanced optimizations to it as well. On the other query engines like Hive and Presto, our recommendations were more around, tuning the thread parallelism at the driver. It does not do it in a distributed way across the cluster, but you can make it multi-threaded at the driver itself. But in general, like, we felt that there was still a lot of scope for improvement, and we felt that we could just reduce this order of n list calls that we are making, and if possible make it O1. And it was possible to implement like an engine agnostic solution, so we don't have to depend on that engine itself to do listing with respect to that engine, for example using Spark context for Spark to parallelize and multi-threads for the other engines. So for that, we worked with the Uber team to implement this feature called the metadata based file listing. At a high level, the idea was that we maintain the list of partitions and files within each partition within Hudi metadata itself, and keep it up to date. As you're doing commits or if you're doing rollback, it should get updated automatically. So how we achieve this is by implementing it as a internal merge on read table. So any commits you do on your actual table are actually internally synced with this table. And this table uses H file as its base file format. So it helps with quick lookups. Uh, and on the query engine side of things, we basically had to make sure that our input format implementations, which is used by Hive, Spark SQL, and Presto Snapshot, can work with this metadata table. And I mentioned that for Presto read optimized queries, though it directly uses its Presto's listing itself along with the path filter. So for that to use the metadata table, we actually are implementing this directory lister interface within Presto itself. So it can do the listing there for us, although that is not yet contributed back and it's still in works. Okay, some of the contributions we made for this feature were basically around query engine side of things to make sure the input format and Presto can use this table, and some other fixes we did. Some of the other contributions we have made until now were around glue catalog support, making sure schema evolution is working with glue catalog, a lot of performance fixes, a lot of data handling issues. Actually, a lot of customers would hit various data type conversion issues, so we had to fix those. A lot of issues around high sync and HBase index, which we are recently fixing. So yeah. So let's see what's on our roadmap ahead. So yeah, we constantly want to upgrade our applications, and support for Hudi 070 is probably our top priority at this time. And it also comes with Flink as an engine support. So we want to make sure that it can work with the Flink offering we have on EMR. And then we want to close out some of the gaps that still remain with metadata based file listing. The data source queries still can't use this feature. So you want to make sure that is closed. You want to contribute our Presto stuff back, and there's still some scope for enhancements on how Spark SQL actually uses the input format. So there's some scope of performance enhancements there. Um, One of the main features that you want to work on this year, which is asked by a lot of our customers, is DDL and DML support. Customers want to be able to create alter tables through SQL and be able to insert and update with SQL on their Hudi tables, and even basically be able to delete or upsert based on any random column, not just based on the record key and the partition path. So in line with that, we also want to preferably work with Uber team for building this column range indexing feature, where we'll basically want to maintain the column ranges, the min max of all the columns for each file externally. So that can ultimately help us, prune out unnecessary files based on the query predicates when we do query planning. And if we go ahead and implement like a feature where you can update, delete based on any random column, so it will ultimately really benefit that feature as well, because we can prune out all the unnecessary files there. Some other features specific to EMR, we want to offer cluster level configuration support. So a Hudi right now, you cannot configure using EMR's configuration API. We want to make sure you can do that. On some other query side integrations we are still evaluating is merge on read support with Presto SQL and incremental query support for Presto, which can ultimately help Athena as well. And this glue schema registry thing came up recently. The schema registry support with Delta Streamer. So this is something we are also evaluating at this stage. Okay, so with that, I've come to end of my presentation. Thank you everyone for listening. Yeah.
All
you
right.
have it.
Thank you, Udit. I think that was a very comprehensive talk to help us understand internals of Hoodie and the features that are supported on EMR and how users can start using Hoodie on EMR. There are some questions. I think a couple of them are already answered. I'll just go over the open questions since we have a lot of them. So the first question is, when can we expect Hoodie 0.6 working with AWS Glue?
That's a good question. Actually, I was recently having this conversation with one of the Glue folks. Yeah, we don't have a good answer. I mean, as soon as they have bandwidth available, cannot comment on another service's behalf, unfortunately. But yeah, I mean, if you really want this feature, the best way is to just create tickets for those specific services, and that's how they get to know that people are wanting that feature. Yeah.
All right. Next question. Nice feature about the custom Hoodie connector in AWS Glue. Is the connector continuously running to stream the changes? That's first part of the question. There are actually three parts of the question. And the second part of the question is, how is DB schema update handled? Will the pipeline break if there is an incompatible change? And the third part of the question is, any plan to upgrade the version to 0.7.0?
Yeah, so the first question is the connector continuously running to stream the changes. So no, connector itself is based off data frame API. So it is not something that is continuously running. The glue job itself needs to run continuously, so that you need to configure to run continuously and pick your changes and apply it. How is the DB schema update handled? With Will the pipeline break? Okay, I think so. The DB, I don't know every nuance because I am not the owner of that, but I think the DB schema or the schema evolution handling and all that should just behave similar to how it behaves with Hoodie right now. So if it is backwards compatible, like similar to like how Avro schema updates work right now. And the third part, any plan to upgrade to 0.7.0? Yeah, again, same thing. I can't comment on this at this point. It's you should really create a ticket for the Glue team about that.
I think I think the schema update question may be around, if there is an incompatible change, what would happen? I think the understanding is, if there is an incompatible change, the job would just fail, right? With it.
Yes, if I'm sure, yeah, I'm sure that's how it works. If there's an incompatible change, it will probably just fail. Yeah.
Okay. I think the next question is similar. How is schema evolution handled with DMS and Hoodie Delta Streamer?
I didn't see this question. Okay. Again, I think same thing as the previous thing we discussed. Similar to how Avro schema evolution is working, I'm sure nothing special there. So if there is, if in your streaming, yeah, if there is some if it breaks, then yeah, your job will probably fail.
Okay. I think we'll take maybe two more questions, and then maybe Udit and Benning, you guys can answer the questions offline. So the next question is, what is the ideal partitioning on S3 for Hoodie to get optimal performance for a batch/streaming job?
Okay, so ideal partitioning as such, I mean, it depends completely on the use case. There's no general thumb rule for that, but I mean, a general suggestion is to have like your data partitioned as much as possible, because it will help you avoid the throttling limits that you reach, which is per S3 prefix. So the better your data is partitioned and equally distributed, the I'm sure the better performance you will get. But apart from that, apart from throttling, I feel the listing performance, at least we have tried to cover it with the metadata listing feature, so that shouldn't hurt you uh, with even with partitioning. going on. Yeah, that's pretty much what I have.
Okay, and then maybe one more question. Any plans for merge and read support on Athena?
Yeah, again, it's a separate service from EMR, but yeah, there is a lot of ask for it, and we are trying our best to get them to support it. So yeah, uh, that's the best answer, unfortunately.
Okay, I think there are a couple of other questions, maybe Udit and Wenning, if you guys can just answer them on the chat box, that'll be very helpful.
Okay.
Okay, thanks a lot, folks. All right. So our final talk of the day is from City Storage Systems. They'll discuss their journey with Apache Hudi, talk about some of the challenges faced, and what's in the future. So Alex, do you want to go?
Yep. Can you hear me well?
Yes, we can.
Right, great. Yeah, so as you guys can see, I'm actually paying tribute to original spelling of Hudi, which did confuse me a lot in the beginning. Like if you go right now and still, search for Hudi, you will see that it's only like HUUDI. You will see that it's number 3 on Google ranking page. And then 2 first numbers will be a surprise, but not a real surprise. All right, so I'm from this company, City Storage Systems. You probably never heard about us. That's by design. I'm not gonna really tell you what we do today because that's not the point. However, another name sometimes you might hear about us is called Cloud Kitchens. Just Google it. If you're interested, hit me up on LinkedIn if you have any questions. Right, agenda. Gonna discuss our pre-Hudi stack, like briefly, talk about why we picked Hudi. Actually gonna go deep on Hudi Delta Streamer in production. There are some questions about schema evolution. I have some answers. I'm gonna talk about learnings. How it started. As any startup, it usually starts with monolith. We're not actual, not that much different. And we had a very simple stack. Client calls monolith. There's big database. Everybody hit in this database. However, at some point, smart people decided that we need, microservices. And then more services got created, queues got introduced, new databases, and then, of course, it's like less complex than reality is, but it gives you an idea, a pretty standard microservice architecture when you have a bazillion of small things which communicate over the network. Everybody tries to have on database, and then get an actually holistic view of all the data becomes a problem. So what do we do? One way, evolution. Again, evolution is interesting because you see it in a lot of presentations from startups. They said, okay, we had this, and then we, added another database, call it data warehouse database, could be a bigger Postgres instance, could be Redshift, could be Netezza, Oracle, wherever you call it. The next step is to add something, then ETL stuff into it, preserving schemas, and then iterate. And then later, when you get to a scale, like you usually go into data lake, lake house, wherever you call it these days, wherever fancy kid, wherever the buzzword is.
Hey Alex, I think we're not able to see your slides.
You can't see my slides. What do you see?
We just see you right now, so
You just see me. Okay, what about, can you see my screen?
yes, now we can see your screen.
Wow, that's interesting. All right, let me back up for a couple. All right, so you didn't miss much. I was just drawing boxes of like standard services and then microservices. Okay, right, and then here's this part with ETL involved. But another way is to do a bit of revolution and go full into distributed stack, like introduce a distributed file system, and then make sure all the changes, usually in a way of CDC, are streamed into this separate storage. And that's what we actually decided to do. What considerations? What are our let's say limitations? What are our thoughts? So the main entity event. So in Uber case, I think a lot of people know you guys use. There's a trip which is pretty common entity. In our case, it's event, which is super complex state machine. And then there might be multiple states for the same, so same event might be represented by multiple states. And users wanted to be able to see both history of those changes and actually latest. Which kind of gives you an idea why we decided that Hudi is a good idea because of absurds. Another interesting part was that our schema is, for this one of the main events, is very, very complex. I'm talking about thousands of lines of Avro schema. They're like arrays, nested structures, arrays of arrays. It's actually pretty crazy to a point that I think one of the versions of Spark just cannot read those files. There's like an issue, and then it just cannot even open it. Our services use protobufs to exchange information. Sometimes they also use protobufs to store them in our databases. On scale side, we didn't want to make a decision and hack it really fast and then go and revisit it in a year or like 5 years. We wanted to pick something that we believe can scale and survive for a long time. Another part of the scale, and I'm not right now not talking about scale in terms of data volume, but in terms of ability to scale organization. I wanted a minimal involvement from data infrastructure team with operations, right? Wanted users to be able to do wherever they want, throw any data in, and then stuff should just work. Wanted schema support to be a first-class citizen. Some of us worked in environments when schema wasn't. Data lakes, right? Schema on read and schema got lost, and it just creates a mess. Wanted our data to have actual schema always. Efficiency, right? Storage is cheap. I had this joke before: storage is cheap, IC2 are not. We wanted to go with object storages just because it's easier to manage. They're good offerings, S3, GCS, cheaper, and then they get in fast enough. And velocity, all right, real time, it's biased opinion. I believe real time is better than batch. So we strive always to find a way to deliver data as fast as we can. So we gravitate towards solutions that also have the same mentality, right? How do we build systems that make it possible to deliver data as fast as possible? And even though we're a small startup, you can see that some of our open source contributions actually support the vision. For example, we contributed in interesting, like one of our engineers contributed Kafka connector to Trino, right? There's PrestoDB, there's Trino, there's Drama anyway. And then it lets us, well, anyone who uses it, to actually query Avro over Kafka Stream. Gives you almost immediate real-time response on a query. All right, so how hard can this idea be? We have Prota, we need to just write it into columnar on DFS, right? And sometimes probably run some simple transformation. Sounds easy. On a high level, right, we implemented this Prota to Avro converter, which pushes data to Kafka, right? Because there's the reason we went with Avro, easier to work with, and then Hudi supports Avro. Well, had primitive support for Avro. We use schema registry to register all the schemas, and after it, data dumped in Hudi, and we use Trino to actually query both datasets in Hudi, and when we need to, also reach out to datasets outside of Hudi, like in some unreplicated storages. Originally, we had to fork the Avro reader to make sure to support the Confluent schema registry we're using. It's still not merged. There's a couple PRs, so there's discussion going on, but hopefully it's gonna land soon. How do we facilitate the write? I believe AWS folks mentioned Delta Streamer, Spark application, can read data from sources, write it in Hudi, supports increments, which is nice, right? Because we don't have to track them, checkpoint, store it with data. It's also pretty good. Supports both inserts and absurds, copy on write, merge on reads tables. Has auto compaction. So this is quite an interesting thing with Hudi, especially merge and reads tables. We use compactions are required. We actually had some interesting challenges with compactions. which I can cover later. Delta Streamer can be used in continuous mode. It's not a real Spark streaming application. It's just something that continuously reads. So you can have an application, Spark app, which just like cycles and reads data. We don't use continuous mode. We use batch mode when we would schedule something, and then once it runs, it just goes away. Just because we're actually happy with a speed of with our current velocity. The big one is it can auto-publish latest schema to Hive Metastore, which is very nice given the fact that we wanted this support for schema and then always know what is the latest and accurate schema of the data. And it even supports simple ETL using Spark SQL. So how did we do it? We actually I think we was the first company which started using Hudi on GCS. How do I know? Because we hit an immediate bug in a part of code that parses Avro log files and then GCS connector. And we probably were like one of the first companies which started running it on Kubernetes. Why do we use Kubernetes when there are stuff like EMR from AWS, Dataproc from Google? Well, because we want to control our destiny and we want to be able to deploy at any environments we want to. Those are main reasons. So YAML, right? Everything starts with YAML in Kubernetes. We try to make it as simple as possible. We even introduced the template generator, which is an application, just a Golang program, which takes our version of YAML, I call it almost YAML face, like interface, and then transform it into something that Helm understands, which pushes it to Kubernetes. And then we use Argo workflows to actually schedule job runs, and we use Spark operator. Here's like very simple example on how we structure data. Again, because we were like so early, nobody ran, like we couldn't find actually anyone else. I think there was one company which we couldn't connect to who ran Hudi on Kubernetes. Might be helpful for you guys, but that's what we ended up doing. Right, we would cluster streams in our Git repository by like some structures. Like that example of the stream that captures queries from Presto, and then we would make sure that like amount of YAML people need to write, engineers need to write is minimal, and then we'll actually transcode it into Helm, which Kubernetes can understand, and like give you an idea. Like rendered YAML is large, 500 lines of code per stream. That's how like extensive configuration is. And then here's example of definitions, right? Super simple. Where to read from, transformation, where to write to. If you look at transformation SQL, that's another thing we're trying to contribute right now. We added this feature to preserve and send Kafka offsets, because we're using Kafka, into like store them together with a Hudi table stream. Super helpful with debugging, especially when somebody says that stuff is not working. And together with the ability to query Kafka directly from Presto, even more helpful, because we can actually even track how late data is if you want to. Some learnings. Generators are great because validation is a big thing. And then mostly writing testable code is much easier than Helm templates. Basic UI, that's what Argo gives us. We try to use original Kubernetes scheduler like cron jobs before, tried native Spark, but it can get stuck the scheduled Spark application. So ended up going with Argo. There are buts. Networking is hard in general. On Kubernetes, cutting-edge stack, we use Istio. It's service mesh. There are gotchas. I'll talk about them. Scheduling is still not signal-based. What do I mean by that? We allow people to pick the size of the cluster or to pick how frequent jobs should run, but I don't think that's the right way. Jobs should run based on SLOs, right? If somebody says, I want data to be available every 20 minutes or 15 minutes or 1 minute, right? The automation or the system should figure out when to schedule, and then the size of the actual Spark jobs or like Flink jobs in the future. We're not there yet. And I was glad to hear AWS guys are thinking about doing multi-writer. We hit this problem when the single writer plus Argo bug created a lot of grief on our side, because you don't want this to happen just by experience. It's a data corruption with a lot of pain. So how did we mitigate it? We use two things. We have this simple application which we deploy on Kubernetes. It wraps a Spark process, and it's responsible for two things. First thing, it guarantees that when the Spark application needs network, it's actually available. So Istio, Sidecar, Envoy is actually up and running. It's not needed in newer versions of Istio, but in our version we use, it's actually required. Otherwise, Spark can launch, no network. Sometimes it can get stuck, sometimes it will retry, or like it just, sometimes it can fail. And another thing, we use etcd to create and maintain leases to make sure there's only one writer. Doesn't matter whether we're writing from different regions or different clouds, right? Want to make sure that one specific location has only one writer, Delta streamer or backfill job. Helped us a lot, actually, especially after we learned it hard way with Argo bug. And then finally, right, Spark application runs and does its thing. So one thing, if you're trying to do Istio, there's like very helpful annotation to exclude some traffic. We couldn't make it work without it. Okay. Here's a better way. There was this question about Hudi becoming a database. I actually like it because I think client engineers, non-engineers, nobody wants to deal with YAML, like all those configuration. It's actually crazy right now in the industry. They just want to write data and then they want to read data. So the way we're thinking about it is that our data layer should be abstracted from those internal implementations, be it, and then just because we have multiple storages, right? And then clients should just interact with API, simple that can do validations. And then internally, right, in this case, we can have a much better control, implement SLO-based scheduler, which can then trigger Delta streamer, and that can consume from the stream. So that's how we're thinking about the future. And now, interesting part, gotchas. So we had issues with schema evolution. Big issues with schema evolution. I would say very large issues with schema evolution, and it's partially because of the way our messages was structured, but then it also gave us an interesting opportunity to learn more about Avro and Hudi internals and like build a better system. All right, so what happens with a message in the system? All right, so we start with a proto. That's original format on a wire, which later transformed into Avro, so a transformer. Not a big deal here. Then, when it enters Hudi, it might get transformed into a Spark data frame, and then later it gets transformed back to Avro, and then it gets enhanced with additional Avro fields, right? Stuff I mentioned before, Kafka offsets or something you see, file locations, for example. Sometimes it just can skip. At the same time, the older Parquet files, there's also Parquet to Avro reader involved, which like reads those Parquet file and feeds them for merging. And there's also Avrolog, which sits on disk for merge and read tables. So it might look innocent, but when formats are changing, there's always an opportunity to break things. And yeah, finally write in the Parquet, of course. And then here's the breakages we saw. Well, Parquet is not one-to-one with what you can do in, let's say, protobuf. Here's like very good example. It's a message with actual no fields. It works in protobuf, it works in Avro. Here's an interesting exception you're gonna get if you try to write it into Parquet. Another interesting one you need to be really careful with upstream evolutions. Null fields, for example, will break it. Like you have message with string, and then it gets written into Parquet with name and then type string. Let's say then you modified it, you created new message, you sending it down the delta streamer, it's a string, it is a not null or not default. Now the catch is that the reader, original reader, will try to read Parquet file using this schema. And when it tries to do it, because in Avro you have writer schema and reader schema, they come together during the read time, it just will not be able to actually read it because it won't find this not null string in all data. Boom, that's exception. Merge and read tables in version we use, we're a little bit behind right now, open source, latest run. A little bit bigger problem because write might happen and then compaction breaks, and compaction is and then compaction, you need to catch it actually and fix it really, really fast. Otherwise, you might end up with a trash on disk. Same thing with deletions. There's like even more interesting problem with deletions because there is this projection feature in a Parquet Avro reader, which is called projection, which we actually was under assumption is supposed to supposed to read a Parquet file given the new schema and only cherry pick fields that you need. However, it's not what's happening. If you try to read Parquet file which was written with Avro schema 1, with Avro schema 2, which misses a field, you're gonna get a very interesting array out of bound exception. So, which was a little bit annoying because we, as you remember, we were trying to be as far as possible from what's going on data producer side, right? Wanted to say, hey, here's pipe, you put anything on one side, it's gonna get persisted, right? So I wanted to have this magic, and then this magic actually beat us. Spark transformation, again, it was mentioned today, and it's actually not perfect. Originally, it required externally defined schema, right? If you read in something, you want to SQL transform it into something else, there is this target schema provider, right? You had to manually specify schema. It was nice, but not for us with a huge schema, right? I wanted something very simple. I wanted to say select, event 1 or something, some field 1, 2, 3, and then I wanted to infer schema. We added this capability. It was called, in a very funny way, it was called null target schema provider. I do think it's a better way to have two schema providers, like source and destination, but that's what it was done originally. Sometimes the Spark library generates invalid schemas and breaks evolution. It's a work in progress to fix it, and it's a deeper problem, right? It's not just Hudi problem, it's Spark problem. Parquet to Avro converter also can generate malformed Avro during the read. Like arrays of arrays, for example, which we have produce recursive structures because naming is broken in an Avro it generates, and Spark just breaks. It looks like it's fixed in Parquet 1.11.1, but also work in progress. We fixed it internally, trying to contribute it back. Here's an example of those problems. Here's Avro record, which Spark generated, right? If you don't know what Avro is, no worries, but that's on the left, it's one that Spark generated. On the right, it's actually how it's supposed to be, right? So type should be null or string, and default should be set to null. That's actually a nullable type, right? That's whatever is on the left is actually not incorrect. There is this issue which has been sitting for a while in Spark land. We had to work around. There's also work in progress diff, which PR, sorry, on GitHub, which demonstrates a way to work around by rewriting the schema on the fly and then fixing all those issues. But again, as a community, we need to figure out what we want to do and then fix this. So solutions, how did we do it? We do rewrite schema. We set everything to optional, default set to null. Even if upstream sends something else, we just set default optional, all the fields optional, even if it's complex hierarchical structure. For Parquet leaf nodes, we ingest leaf nodes, fake fields to support this use case for marker fields. And for Avro messages, we also make sure that, super important, when we read messages from Avro, we make sure we only read message with the schema it was written, not like latest schema provider. You actually have to use correct reader. Again, work in progress. There's like back and forth on GitHub, but hopefully it's going to be merged so everybody will be able to enjoy it. And the latest is we had to patch Parquet Avro reader to make sure we can support deletes. There might be a better way. We'll invest more time into it, but that was one of the ways to properly support deletes. Yeah, some fixes, as I mentioned before, were open source, some underway. But, like really happy to work with community and then help to make it better. That's it from me. Right. Again, as everybody else, I put in this recruiting message. So if you're curious what we do, you know where to find me. And thank you for this opportunity to speak at the meetup. It's a rare occasion in our COVID time. Thank you.
Awesome. Thank you so much, Alex. That was a very cool presentation. Lots of details, lots of interesting takeaways. Something we have in common, I also got the hoodie swag along with you. So like, we're both sort of rocking that hoodie.
Right? Old schoolers.
I know. So there are a few questions. I think there's one question which maybe you can help shed some light, which is when will we be ready for hoodie with GCP? I think you guys are running with GCS, but if you have any info to add on that, that would be great.
GCP, what do you, I guess I'm not sure what the question is, right? We do run it on GCP. We never ran it. Well, so, okay, I'll take it back. We ran it on Dataproc originally. Did it everything manually. So I'm not from Google, so I don't know where they're gonna support it. I think they do support it, but we never used Google infrastructure actually to run a hoodie like EMR. It was always either our custom-made image which we ran with Dataproc, or we ran on Kubernetes. And because file systems are pluggable, you can point it to GCS and it just would work because they're like already fixes in the open source fixes in the upstream. Yeah, I think we just merged latest because I think like if you go to 0.6, it might not work. There was an issue, and I think 0.7 master right now works fine.
Got it. Thank you. Next question is, are you using regular Delta Streamer or multi-Delta Streamer? Do you process your tables in parallel?
Yeah, we use, I think I mentioned it, we do not use multi-Delta Streamer. I said we don't use continuous mode. Yeah, we use a separate Delta Streamers. Each stream gets on Spark job at the moment, which is scheduled using Argo. And then one of the points what I was trying to make, it's not great, right? Because we want to be efficient on resources, and some tables have a bunch of data, some tables have no data, some people use Kappa architecture, which means, hey, I'm gonna dump, billion rows and like whatever amount of rows in Kafka, and then your Delta Streamer, which was sized for some workload now, slow. So multi-tenancy is a large problem. We don't have a solution yet, but we're working on it.
Great. Next question. Nice presentation. Is Delta Streamer your main Spark ETL tool? How complex is your transformer SQL?
Yeah.
Also, how are you dealing with multiple upstream tables on your SQL transformation using Delta Streamer?
Oh, well, good question. So we don't have yet a very sophisticated, so we do not use Spark, I would say, for ETL at the moment. We actually trying to use Flink because we want to be on real-time side. And while Spark can be run in real-time, it's actually might be quite painful experience, speaking by experience. So the way we're thinking about it, right, we use Spark at the moment because Spark was the only engine with Hoodie, right? Once Flink is ready, we'll probably switch to Flink. And the way we're thinking about it, again, like going back to my slide was, nobody wants to run Spark. Nobody wants to run Flink, right? They don't care. I'm actually had a different presentation talking about our Apache Pinot and Presto in Trino commits. I almost believe that people want to say, data is here, I want to get it there, move. And then magic happens. Presto, Flink, wherever engine is executed. So the answer is we have multiple pipelines. We mostly Flink heavy. Hudi is usually used as a Spark used just to land Hudi jobs. Even in our ETL, we have a hybrid because Presto cannot write it. So we read using Presto and then write using Hudi. We do those tricks. How do we deal with multiple upstream tables? Well, for Presto, it's not a problem. For Spark, I don't know the answer, honestly. We wrote, again, some custom stuff internally to support those, we call it incremental materializations. So we can join multiple Hudi streams, but that's a topic for, whole meetup, because it's pretty tricky, actually.
Yeah, I think this is a question from a colleague, and I think that would be useful to learn. Alex, maybe we could take this offline. I think we have some use cases around those as well. Would love to learn.
Yeah.
Maybe in the open source community.
Yeah, absolutely.
So the last question is, why not continuous mode? Is there any downside?
Why not continuous mode? So it's not like it's downside. Because we use elastic infrastructure, right? We don't have compute which is static, right? When you physical data center. So we're actually trying to make sure we utilize it. We heavily rely on autoscaling side on Google, inside Google Cloud. And then so like cluster constantly expands and contracts. And then running smaller workloads gives us like better control. It definitely can be implemented even in continuous mode with some coding. We just didn't get to it, right? With a new way, we really want to get to SLO-based scheduling. There was this internal proposal, and we'll need to evaluate like what can be done, right? Because it takes time for Spark to launch. Like Istio to launch on Kubernetes, sometimes it's a minute, and it would be much cheaper if we have a way to have multiple pipelines and actually push push a request into what to run inside those runners, like a thread pool, Spark, call it Spark pool, and do it dynamically. That's a thinking, but again, that's not implemented, still in design phase.
Awesome. I think we're right on time. Those are all the questions. So thank you so much to all the presenters for all the awesome presentations. I myself learned a lot, and thank you all for attending. Lastly, I'll just share my hiring slide again. Please, if you're interested in working in these areas, please reach out to us at data-lake-jobs@uber.com, and look out for any future meetups. All right. Thank you so much.
Thank you. Bye.